Hi, I'm Guillaume Bury, and today I'll be talking to you about Dolmen. So, first question is, what is Dolmen? And, basically, Dolmen is a parser and type checker for SMTLIB. But it's a bit more complex than that, of course. Basically, Dolmen tries to be a conformance checker for SMTLIB. So basically, it tries to parse and type exactly what the SMTLIB specification defines as being the conformant with SMTLIB, which is a bit different from most what happens in most solvers, where basically the solver parses and types SMTLIB, but mostly what the solvers can actually handle and solve. And Dolmen, so as a parser and type checker for SMTLIB, is available basically as in three different ways. First is a command line binary, so you can call Dolmen on a file just like you would call a prover on a file. But Dolmen also offers an LSP server, so basically it's a text editor plugin, so that you can have the warnings and errors that Dolmen returns directly in your editor when you're editing files, SMTLIB files, and so on. And lastly, Dolmen is written in OCaml, so it offers an OCaml API for projects that want to use Dolmen to parse and type problems. So that's good, but one question would be, why is there a need for a conformance checker for SMTLIB? After all, the SMTLIB syntax is relatively simple. It's basically just S expressions. So it's not that complicated, but as it happens, some logics have restrictions that are quite complex to check. Examples of that are linearity constraints in arithmetics, which, as we'll see later on in this talk, can sometimes be surprising and cause quite some errors. Some logic in SMTLIB also have restrictions about which sorts of arrays can appear in the problems, and so Dolmen will be able to check that kind of things, which is otherwise not always trivial to do. And lastly, SMTLIB has some degree of polymorphism, and it's sometimes can be a bit not trivial to check polymorphism and things like that. But more importantly, I'd like to say that as long as there exists a standard, so the SMTLIB standard or specification, it's interesting to have a way to check conformance with that standard. Because if the standard exists, it's because it's useful. And just this fact gives interest in being able to check whether a file conforms to the standard. Mainly because some new solvers may rely on files respecting the standard, and so it's interesting to see how a file respect this standard. So that's Dolmen in a nutshell. And basically in this talk, I'll talk, it's in two parts. First, I will present a bit to you how Dolmen works in practice. So, how the command line binary behaves, and a small demo of the LSP server, so that you can see how nice it is to have feedback directly in your editor, and hopefully want to try it. And then I'll talk a bit about what happened when I ran Dolmen against the whole SMTLIB. So basically, how many files in the SMTLIB didn't respect the standard, and why, and how Dolmen compares to another prover in terms of performance when we try to check files in the SMTLIB. So first, Dolmen in practice. So Dolmen is quite simple. I mean, it's particularly the Dolmen binary. It's just like a solver which only does parsing and type checking. So you can invoke it on the command line, and either you get an error or warning, or you get nothing and everything went well, and that means that the file is conformant. As I said before, checking that a file is conformant can be a bit tricky. So for instance, linearity, which will be actually the main source of problems with files in the SMTLIB. So if we consider the following file, so you have a really simple file in linear arithmetic and in quantifier-free linear arithmetic, you have two constants, and you just have silly assertions, but with a multiplication. So basically, I think we can all agree that this term is linear. Basically, any solver handling linear arithmetic will be very easily able to understand and handle that kind of term. However, and we can check that if we try and run CVC4 on it using even the strict parsing option, then CVC4 gladly accepts that problems and no problem, and is very happy. However, if we look closely at the specification of QF-LIA on the SMTLIB website, we can see that in order to enforce linearity, all uses of the multiplication, the store, is forbidden except in the following condition. So basically, we are allowed to use multiplication when one side of the multiplication is numeral, so a number that is known when you read the file, and the other side is a free constant. So basically, either a variable or symbol. And the problem with that is that if we look at our expression earlier, here plus AB is not a free constant. It's a complex arithmetic expression. And so if we read the standard in a very strict way, that expression is not linear, or at least is not accepted in logics that only have linear arithmetic. And that can be surprising. So I won't take a stance, so we could argue that maybe the standard could be a bit more lenient and accept more expressions as linear. But it's not really the point here. The point is that, well, it's interesting to try and see if we can really check whether files conform strictly to the standard. We could talk later about changing the standard, but first we have to see how much of a problem or what happens when we try to adhere strictly to the standard. And so if we run Dolmen on that example, we get the following output. So basically an error, and Dolmen says that this expression, so if you look here, you have the position information, so line 4, characters 13 to 26 is basically that multiplication. Dolmen tells us that it's nonlinear expression, and to help in cases such as here, where it's not really intuitive why this is not a linear expression, Dolmen can provide hints to explain a bit more the error. And in this case, basically, Dolmen explains that in linear arithmetic, when you have a multiplication, one side is expected to be an integer or rational literal, and the other side is expected to be a symbol, so a free constant, a variable or constant. And that here, in this example, instead we had an integer coefficient and a complex arithmetic expression, because we have a plus AB, which is not a trivial arithmetic expression. So really, the point here is to try and give as much information to users as possible for them to see how to fix the problem. Right, so basically, that's a quick overview of how the binary works. Basically, we also have an LSP server. So LSP stands for Language Server Protocol and is a text editor extension developed and supported by Microsoft, but that's been adopted in basically all editors I know of, so Vim, Emacs, VS Code, and every other editor I think supports LSP. And LSP allows you to more easily implement text editor extensions to have feedback directly in your editor. So if we look at a demo, so here we have some parameters before, and you can see that using the Dolmen LSP, we have in our editor directly feedback about the error. So we have so the way this information is presented may differ based on your editor, but basically you can have the location of the error highlighted and the error message. So here you have basically the same error message as we saw earlier. And we can try a bit. If we, for instance, say that, well, we'd like to be in a nonlinear integer arithmetic, well, now everything goes well, and we don't have an error anymore. We can go back to linear. We can try other things. So for instance, in SMTLIB, it's forbidden to declare multiple times the same constant name. And so here we can have an error saying that, well, B was already declared and it's an error to define the same constants twice. So it's really useful to have that directly in your editor. It helps you not have to go back to a terminal, run your tool, and then go back to your editor. It's really convenient, and it's usually quite quick to set up. So we also can have warnings with Dolmen. So let's see. If you look at this file, so basically here we have a constant that is declared, and then we rebind it basically. So we have a local variable a which shadows the constant I. This is allowed in the SMTLIB standard. But it can sometimes be dangerous to do that, because sometimes this shadowing is intended, and sometimes it's not so much intended. So if we run Dolmen on that example, we can see that we get a warning. Everything goes well. I mean, Dolmen successfully checks that the file is okay, but we still get a warning saying that, well, the variable a shadowed the constant declared at line 2. So, and we have the two locations. And of course, if we go in our editor, with LSP, we get the warning here, nicely. So that's basically the binary and the LSP server in a nutshell. So if you want to try, it's really fun to try and see in different examples how Dolmen behaves, and so on. So yeah, here's Dolmen, and there isn't really much more that is convenient to present in a talk like that. So what's more interesting to talk about though is what happens when basically you run Dolmen on the SMTLIB benchmarks that are provided on the SMTLIB website. So basically there are 363,750 files in total. And if you run Dolmen with a strict, trying to check strict conformance with the standard, there are quite a lot of files that fail to type check, basically. So about 2% of files, so 8,465 files. And if you look a bit closer at what is the error on those files, mostly it's linearity check that have failed. And it's reasonable. In most cases, the linearity check fails because the term doesn't conform to the specification, but is actually linear. Fun anecdote. If you look back at the specification, basically here, you'll see that terms such as 3 times 5 technically are not allowed in linear arithmetic. So not that much of a problem, but maybe it shows how easy it is to write expressions that one would intuitively consider linear, but that are not linear according to the specification of linear logics in the SMTLIB. So for that reason, Dolmen has a strict options which can be set to false to make Dolmen a bit more lenient toward a bit more lenient, mainly concerning the linearity check. So when we use Dolmen with a strict equal false option, we now get a much smaller percentage of files that fail to take check. So about 350, which makes up about 0.1% of files. And it's interesting to detail a bit what are the failures in this file. So that's what I'm going to do here. So first, there are 23 files in the incremental version of QF of LIA, where there are arrays that are so different than array in int. So in QF of LIA, the only sort of arrays that is allowed is array int. And if I remember correctly, most of the arrays that trigger error here are of sorts array int, something like that. So here we have truly an error, and that's a problem because it's clearly wrong according to the spec. So now we have a bit more problems concerning linearity, and linearity in the integer defense logic, which is again a bit different, where basically you're only allowed to have subtractions, but sometimes contain additions on certain files. So here, if I remember correctly, in these files, the terms that contain additions are basically let bound, and if you substitute the term, you could then simplify expressions into forms that are conforming to the defense logic specification. But basically, even if semantically the problems are in the defense logic fragment, they're not really conforming to the specification, and it can be surprising. Again, in defense logic, we have additions between arbitrary terms. So one thing of note is that the defense logic in IDL and UF IDL is not the same. Basically, the specification of the defense logic is different, which is very helpful and not at all confusing. But in these fragments of defense logic, you can have additions, but only one side of the addition can be something that is not a numeron. And the NAND files where you have like something like x plus y, which shouldn't be allowed. Now we get on files that have problems with linearity. And so basically we have files which basically express some kind of rounding modulo some integer. So basically we have variables where you multiply the variable by division, which this could be written as that expression, so using modulo. But even still, with that rewrite, we're still in a linear logic here, linear arithmetic logic, and so modulo is not allowed. So we have a problem on files in here, which use basically modulo under the hood. We have truly nonlinear expressions here, where basically we have on one side of a multiplication the size of a list, and on the other side conditional. So even with the most accepting criterion of linearity, basically this would be rejected. So thankfully there are only two files in here. So next we have a few files that use rational coefficients, but which fall slightly outside the spec. So basically, having the minus before the division is not allowed, and according to the spec, the minus should be on the on the top of the division, basically. So it's really just nitpicking at that point, but well, that's what the specification says. We have a bit more files that use Euclidean division in QF SLIA. And basically, even if there is no official description of the logic, we assume that just like every other linear logic in the SMTLIB, which forbid use of Euclidean division. So does the QF-SLIA logic. So again, problem with linearity. We have files in QF-SLIA which use quantifiers, but basically these quantifiers are used to express that some term is pair. Basically, it's a multiple of 2. And what's interesting is that actually for every instance of such a formula, you could lift the exists at top level, introduce a new constant symbol, and just replace v by the constant symbol, which will be implicitly existentially quantified, like pretty much all constant. So those could be rewritten to not use quantifiers, and that would help. So, and I assume that's why at least some solvers do not error out on those benchmarks, even though they contain quantifiers in the quantifier free logic. And I think that lastly, we have a lot of files in LII which use division or modulo, which is again not allowed in arithmetic. So here we can see that most of the problem we have are basically a problem with linearity in arithmetic. Basically, almost all of them except the files in QF-AOF-LIA are variant of linearity in arithmetic being broken. So that's a summary of the files that are not conformant in the SMTLIB benchmarks. And another point, so here's the summary. Another point that's interesting to look at is performance. Now that we have seen that Dolmen is able to check files. So I ran Dolmen and CVC4, CVC4 in parse-only mode, on the whole SMTLIB, basically all the benchmarks in the SMTLIB. And so CVC4 in parse-only mode takes on average 0.07 seconds on each file. So it's an average, of course, here. And if you run Dolmen in lenient mode, so strictly equal false, we get an average of 0.04 seconds. So here we see that Dolmen is significantly faster than CVC4, which is good, particularly because Dolmen only checks things. But well, basically in so Dolmen only checks things, but it's interesting to note that Dolmen checks more things than CVC4. For instance, CVC4 in parse-only mode doesn't check linearity constraints. I think it only does that when it goes into the pre-processing step. So we have Dolmen, which is faster and check more things than CVC4, which is nice, as long as performance goes. And if we use Dolmen to only parse files, so we deactivate typing, we see that basically it speeds up Dolmen by a factor of 2, which indicates, it's not really important, but basically we can see that when running Dolmen on a file, basically half the time is spent reading the input and creating the syntax tree, and half the time is spent checking the types for the syntax tree. And I have a graph of the cumulative time used by each solver. So we have here on the x-axis the time spent cumulatively, so the sum of time spent checking files. And here on the y-axis we have the number of problem solves. For this graph, the times are sorted before being added for the cumulative thing. So basically, you want to be as much top left as possible. Basically, if you're here, that means you check all the files in the least amount of time. And with that, so we have CVC4 in blue here. We have Dolmen, which does everything in green here, and in purple, that's type equal false. And the graph allows us to see that it's not just a strange repetition of problem-solving times that differentiates Dolmen and CVC4, but really that basically almost all of the time, Dolmen is slightly less than twice as fast as CVC4 in parse-only mode. So that's good. So that's the performance in terms of time. I haven't had time to measure performance in terms of memory used, but some preliminary examples that I ran indicated that Dolmen consumes more memory than CVC4, about twice as much, from what I recall. So that probably explains a bit of the why Dolmen is faster. It's a bit of a time-space trade-off, I guess. But it shouldn't really be a problem, considering that it doesn't use that much RAM, except on truly gargantuan problem. But even then, we just check the file, so really it's not that much of a problem. So that's the talk. If you want to try, Dolmen is available on GitHub at that address. I really encourage you to try. There are binary releases, so it should be really easy to just download the binary and try it yourself. I didn't mention that in this talk, but Dolmen doesn't only support SMTLIB, but it also supports other languages. So for now, it's mainly TPTP, the proposition's own language format, and Emacs that can be checked with Dolmen. I'm in talk with maintainers of the SMTLIB benchmark collection, and Dolmen will very likely be used as one of the many checks that will be performed on the new benchmarks starting soon. So that's nice. And lastly, try Dolmen and do not hesitate to submit issues if you find any bugs, surprising behaviors, or if you want to request support for extension of SMTLIB and so on. For instance, Dolmen already has support for the polymorphic extension of SMTLIB 2, which was presented at, I think, the SMT Workshop like 2 years ago, with Altergo, for instance. So Dolmen already supports one extension of SMTLIB, and I'd be very happy to add new extensions to the checks that Dolmen can perform. So thank you for listening to me, and hope you use Dolmen. Bye.